Okay. Let me say that again. Today we're going to assign point groups to molecules and learn about character tables. And so let's go back a little bit and talk about how the particle in a box wave functions could have been analyzed this way. Now, when you did the little small numerical solution spreadsheet where everything was on the same page, and at the bottom of the wave functions, I had even and odd. Do you remember that? The little row that said even and odd and so on, and even times even is even and odd times. That's what this is, okay? So if we go with the blue wave function, psi1, if we go left to and evaluate the function, it's positive. If we go right to and evaluate the function, it's also positive and has the same magnitude. So that by definition is an even function, okay? And so we would assign that even. Now, we have these things called character tables, which have this, what we've done is an inversion operation on that function. And our answer, when we invert it, has the same magnitude. And so that's a +1 character. You see that for this even function, psi of x is equal to +1 psi of minus x. So plus x and minus x have the same value. So we have a +1. So that means that this wave function can be labeled with AG. So this, what we have, is called a character table. And it has all of the symmetries of everything in the molecule. And so we can label this psi1 as AG. And they'll pop up in a minute, but in your notes you have some blanks over here. You find it, yeah. So we could label this one AG. What about the red one? So we go left, -2, it's a positive value. We go forward, 2, it's a negative value. Same magnitude, the only difference is that it's flipped sign. And so that's this -1 character in front. You see the odd function, psi of minus x is equal to, -1 is the opposite of psi of x. On both sides of that function, they're just mirror images of each other, but negative. And so we have a -1. So we would label this function with AU. So the red one would be labeled AU. And now let's look at the green one. Can you just look at it and label it AU or AG? Yeah, AG. Because you just look at its behavior, on both sides of 0, it's a mirror image. Okay, so this one is AG. Yes. GNU is a German word for gerade, which means even, and ungerade, which means uneven. Yeah. So GNU mean even and even and odd. Yeah, even and not even. Yeah, and so we're learning some German today. So now you're trilingual. Yes. So even for the psi1, odd for psi2, even for psi3, and it alternates all the way up. Okay. Now, this can be very useful, and I'll show you. Now, this top row is the only even row. We'll see other character tables where in the bottom rows, all other rows are odd in a character table. Okay. So this is useful because we have these properties of even and odd functions. So look at this. An integral of an even function is not equal to 0. That's great. So I can just look at the symmetry of the function and know if I take the area under that curve, I'm going to get a non-zero number. And then an integral of an odd function is equal to 0. And I can multiply functions by each other and change the symmetry of the integrand. So if I had 3 functions multiplied by each other, like I do in a transition dipole moment integral, I can calculate the symmetries of those and learn to see which is going to be 0 and non-zero. So let's do this. Remember we had this allowed and forbidden transitions. We did this by hand with the analytical solutions. And we did it in Excel numerically, but here we're doing it in symmetry. So let's look at this transition here. So let's put our symmetries of these different things. So this n = 4 wave function is AU. So that's going to go here. the x-axis, let me just change AU. The x-axis, so let's just look at our x-axis that's representing light. I have a positive 100 and I have a negative 100. So if I go to the right 100, it's a positive 100. If I go to the left 100, it's negative. So it's an odd function. Does everybody understand that? Well, in this system, I would label that odd. That would be AU. And then the n equals 1 is AG. And remember, this integral over all space squared, that's the transition dipole moment integral. That's going to tell us what the intensity of this function is. So we want to know what this is going to be. So here's our character table. And more importantly, for this point in our lecture, this is the direct product table. So this is all of the rows of a character table multiplied by each other, okay? And all of the results of those. So we have all of the possibilities, AG times AG, AU times AG, and AU times AU. Now they typically write these as triangular tables, right? They don't fill the whole thing out because they're lazy, okay? It's symmetric. So this is also AU right here. But they just don't put it because they, I guess they're saving ink. I guess. But anyway, you'll see that triangle. So if you try to do AG times AU and you see nothing there, well, just do AG times this AU and you see that it's AU. Okay. Or you can fill out the rest of the table. But I would just say, if you're trying to go and you end up in the blank area, then just flop the 2 and go down into the non-blank area. So we have this AU times AG. So we come down here, AU times AG is AU. So that's going to go right here, AU. So that's the result of those two functions times each other. And so we've eliminated one of them. We have the symmetry of that product. Now we've got one more product. We do the symmetry of this product. AU times AU is AG. So this one comes up over here, AG. Now remember, we said that the top row was even. So the integral over all space of an even function is non-zero. So this integral squared, it doesn't matter that it's squared, but we can leave the square on there, is not equal to 0 because it's even. Yes?
It doesn't matter like where is that, right?
Yeah, but typically we do it from right to left. Yeah. And so in all of ours, they're not only right to left or left to right will give you the same answer, but they're even commutative in our situation, but matrix multiplication is not always commutative. So we just always do it, initial state, final state, and light. Okay. So we're going from 1 to 4 in this example. Yeah. And so this is allowed by symmetry. So I can tell that it's not 0 just by the symmetry. And look how small this little piece of paper is I have. That's about the size of a Post-it note. And this took 4 pages of math to learn. Yeah, so the symmetry that's why we like it, because it allows us to cut to the end of the problem and know if the answer is 0 or non-zero. Let's do this one. So n equals 3 is AG. Light is AU, and n equals 1 is AG. Okay. We want to know, I know it says equals 0 here, but we're just doing the problem as if we don't know what it is, okay? So we do these pairwise, AU times AG is AU, and then bring this AG down, and AG times AU is AU. This is an odd function, so the integral over all space of that odd function is equal to 0. So this is forbidden by symmetry. So symmetry allows us to determine if a spectroscopic transition is allowed or forbidden. Now you may say, but we can calculate it by hand and we could calculate it in Excel. No, that's for a particle in a box. That's for one dimension. Symmetry allows us to go to 3 dimensions. And we don't have to worry about 3-dimensional integrals, 3-dimensional derivatives, all of that stuff that you did in Excel. We can't do that for water. We can't do that for ammonia. But we can do this for water and ammonia. It works for the particle in a 1D box, very simply, very easy to see. And we can confirm it by our actual calculations here. But now we can move this into 3 dimensions using point groups. So this is the need for symmetry. We start with the Lewis dot structure. And y'all need to be good at that because that's always at your defense. So you always need to be able to do Lewis dot structures. And by that I also mean the 3-dimensional, the hybridization, like get that ammonia is, a trigonal pyramid and things like that, and methane is a tetrahedron. And so we get the geometry of the molecule. And then from the geometry we get the point group. And that point group is super important. Once we know the point group, then we've cracked the puzzle. We can open the safe. Okay, so these are the character tables over here on the right. And the character tables allow us to determine the symmetries of the molecular motions. So the vibrations of the molecule, whether they're Raman active or IR active, very important for folks that do Raman. The symmetries of the molecular orbitals, so the vibrations of the electron cloud. Is the HOMO to LUMO transition allowed or not? Is it going to be a colored substance? That kind of thing. Determine the interactions of equivalent nuclei in NMR, or intensity patterns in the infrared. This can be determined with symmetry. And then from those character tables, we can do the direct product tables like we just did and determine the symmetry selection rules. So our symmetry selection rules for the absorption, we did analytically by hand, and we did it numerically in Excel. We got the same answer for those of plus or minus 1, 3, 5, 7, and so on. We can get that, what we just did with the little Post-it note size calculation, we can show that it always has to go from AG to AU or AU to AG. That's the only time it's allowed. And immediately we get the delta N of 1, 3, 5, 7, 9, all the odd ones. So we immediately get the selection rules on a calculation this big. That's great. Okay. So, but we can't do really easily 3 dimensions numerically or calculus-wise, but we can use point groups. So this point group is a symmetry, it's a group of symmetry operations of a molecule. Like CO2, if my head is the oxygen and my hands are the hydrogens, it has a C2 rotation axis. They can rotate 1/2 of a turn. So that's what the 2 means. So 360 degrees divided by 2. So 180-degree turn is a C2 rotation. And you see this hydrogen and this hydrogen change places. So like if you close your eyes and look at the molecule and then you open them again, it doesn't look like the molecule's changed because the hydrogens are identical. So you can rotate it and look at it again and say, yeah, the molecule's unchanged. If I took the water molecule and rotated it 1/4 of a turn, so 90 degrees, and you looked at it, it's changed, right? Because now the hydrogens are pointing out at you and they were like this. So that's what we mean by remain unchanged. If we rotate it 1/2 a turn, the molecule is back to what looks like its original position. And so we say it possesses a C2 axis. Because if I rotate it 180 degrees, so 360 divided by 2, that C2 axis, the molecule is back to where it was, even though the hydrogens have changed places. You could also think of just rotating the labels. So this is hydrogen 1, this is hydrogen 2. If we rotate the labels, do those labels hit a hydrogen? Like hydrogen labeled 1 and hydrogen labeled 2, do they swap labels? If they swap labels, they have that operation. If I did a 90-degree turn, the labels would be out here and they're not even on any hydrogens. So how can I rotate the molecule to get the labels to change places? That's another way to think about it. And essentially you're leaving the structure unchanged and seeing if the labels can be swapped. That helps some people. because they don't picture the rotation of the molecule, but somehow they can picture the rotation of the labels. Okay. Now it has to be a hydrogen. If this is a hydrogen and this is a chlorine, you know, and you swap, now H1 is on a Cl and that doesn't work, and Cl is on a H and that doesn't work. So that could be the identical atoms changing places. The center of the mass of the molecule is the point in point groups. When we talk about point groups, these are single molecules in space, centered at the, you know, with the center of mass in a particular Cartesian frame. There are space groups. So for crystals, those in inorganic, doing research and so on, you might learn about the space groups of crystals and so on. There are other symmetry operations that apply to space groups that don't apply to point groups. And so we're not going to get into that, but there are more symmetry operations than just what we're covering, but they apply to space groups, not point groups. Then we're going to have this phrase, this notation called the Schoenflies notation, and that's what you've learned if you've done group theory before, of like C3V or C2V or tetrahedral PD and so on. And we're going to use a flow chart to determine the point group of a molecule. So here's a flow chart. We have a molecule like water. We come in and we answer the question, is it linear? No. So we would come off of that diamond over here. Does it have two or more unique C3 axes? And so water only has two hydrogens that could exchange. It can't be a C3. If I move it a third of a turn, like 120 degrees, there's no hydrogen there. So it doesn't have any C3 axes. You can't rotate it this way and change the hydrogen to the oxygen. For one reason, it's not an equilateral triangle. But even if it were, you'd be moving a hydrogen to an oxygen. That's not going to work. Okay? So it doesn't have multiple C3 axes. And so we would say no. So we're down on this page. Does it have any C rotations at all? The answer is yes. It has a C2. Water has a C2. Okay, so we'd say yeah. Select the highest C axis. Like maybe you've identified multiple ones. Water only has the one, C2. And this question says, are there N C2s perpendicular to that C2? So do we have, on water, we have this molecule that's bent. There's a C2 axis here. Are there C2 axes that are perpendicular to it? That would rotate the oxygen down. No, there's not. And there's one here that would also rotate the oxygen down. So there's not a C2 axis perpendicular to this C2. So we would say no to that question. Does it have a sigma H? Now this is a reflection plane. So we have a rotation axis, and the rotation axis, we always point up. The one with the highest N, we point up. And this axis horizontally would be perpendicular to that rotation axis. So this would take the top of the molecule and reflect it into the bottom. And there are no hydrogens above water to reflect down into the hydrogens below. So we would say no to that. Does it have any mirror planes that are vertical? So we have the C2 axis going up. Are there mirror planes vertical? Yeah, think about water. So here's the oxygen, here's the hydrogens. I can reflect the hydrogens into each other with a plane right here. And it's a planar molecule. So the front of the hydrogens can reflect into the back of the hydrogens, and the front of the oxygen can reflect into the back. You know, they're spheres. So the front and backs of these atoms can reflect into each other. So there's two mirror planes, one this way and one this way. So we would say yes to that one, and we end up here. This is a stick structure of water. So it's C2V. So that N is 2 for water. Yeah. So this is how you use the flow chart. We'll get lots of practice. I just wanted to walk through the flow chart for water. So these are the character tables. Once you identify the point group, like if you determine an octahedral complex, these are all the symmetry operations that are in an octahedral complex. And these are all the different symmetry rows that they have. All the different motions of the molecule, all of the different molecular orbitals will have a particular symmetry that ties to one of these rows. And when we're doing multiplications of these rows, you know, we have this integral over all space of an even function is non-zero. The only even function in these character tables is the top row. So anytime we do these multiplications, if the final integrand doesn't contain the top row, then it's going to be 0. It can have all kinds of things. It can have EU and T2G and EG and A1U, all in that integral added to each other. But if you don't see the top row, and in this particular case for octahedral, it's A1G, if one of those elements isn't A1G, then the whole thing is 0. And that can determine then that that transition is forbidden by symmetry. So let's just leave what I said again. The even functions are non-zero. The integral overall space of an odd function is 0. So let's look at the character table. I'm going really fast because I want to get to the point group practice, okay? So that's the Schoenflies notation. That's the point group. That's C2V. These are called Millikan notations for the irreducible representations. We'll understand in a minute, or in a future lecture, what reducible and irreducible mean. These are the characters. And these are useful rotational and Cartesian basis functions. So this would tell me the symmetry of X polarized light in this point group, or Y polarized light. And Z polarized light. Or rotation around the Z-axis would have A2 symmetry. Rotation around the Y-axis would have B1 symmetry, and so on. This also would be this Y here would be the symmetry of the vibrational motion, which is sort of going left and right. So if this is the Z-axis, the X-axis, the Y-axis, and I have the asymmetric stretch in water, look at my head and my hands. They're moving along the Y-axis, back and forth. And so that dipole derivative would be moving along the Y-axis, and it would have Y symmetry. It would have B2 symmetry. A p orbital. So if I had the p orbital on the oxygen atom, and it was the py orbital, so this side was shaded, this side was not, and it's oscillating like this. It's oscillating along the Y-axis. So that py orbital would have B2 symmetry. Pz orbital oscillating up and down would have Z symmetry. So we have all of those things here. Raman interactions. So we might have scattering photons. I think of it in a sort of a classical model where a photon comes in polarized in the X direction, and it leaves, it scatters off polarized in the Z direction. So that kind of interaction would be a B1 interaction. So we could have that be our light, scattering interaction. Now these vector representations of the point group we're going to get to in a future lecture. But when you hear me talk about irreducible representations, those are the rows in the character table. Okay. And we'll do the reducible representations next time, but I just want you to mainly connect this this irreducible representation of the symmetries are the rows in the character table. Just to emphasize that. And then we get into the Millikan notation. These different rows have some conventions associated with them. It's A if this is the Greek character chi. So let me put it up here. Chi is equal to character. So it's just it's, if you were to write it in Greek, it would start with character. So now we're learning German and Greek. Okay. So if the character under rotation is a +1, then it's an A group. You can kind of see that here. The character under rotation is a +1. Down here, that character is a -1, and so it's a B group. Okay. The two-dimensional rows are labeled E. Now, I've had some problems with the way science does this in the past. This is the worst example, where you have the same letter mean two different things. Okay, in thermodynamics, you have Q representing the partition function, and then later you get into heat and work, and Q is typically used for heat. But at least they're different parts of the semester, right? It's the first part of the semester, Q is partition function. Later, we get into heat and work, it's heat. It's on the same table. We have an E, which is the identity operator. Which is essentially multiplying by 1. Okay, so all the Cartesian coordinates are multiplied by 1, so there's no change. Okay, every mathematical system needs to have an identity operator. Like in matrix math, it's just the diagonal of ones. You know, in this case, so the E operation is identity. That's the symmetry operation of nothing, of identity multiplied by 1. But it's also this row here. The Mulliken notation has an E too, and that's a two-dimensional row. You see that on the E, the X and Y's are always coupled. See here, B1 and B2, the X and Y are split apart. Okay, but here on E, the X and Y are coupled together. It's because on symmetric molecules, there's no difference in X and Y in terms of energy. Okay, so this is a degenerate set. So the X, say if this is molecular orbitals, the X molecular orbital would be the same energy as the Y molecular orbital because we have threefold symmetry or better. We have a symmetric top system. So I'm sorry about that. I didn't do it. So it's really context in the table. So if you're talking about a row, E is a two-dimensional row that contains X and Y and some other things. If you're talking about a column, the E column is just the identity column. We never really use the identity column. So the one you're going to use the most is the E row, the Millikan notation. And then the subscripts G or U only exist if the molecule has inversion symmetry. So G is gerade, German for even. U is ungerade, which is German for odd. And so you see up here water for C2V. There's no inversion operator on this set of symmetry operators, but here at D3D there's an I there, and you see the positive ones here under I are all G, and the negative ones under inversion are all U. Okay, so that's where the G's and U's come in if they have an inversion center. So let's practice. We've got a little bit of time. Let's go to SimOtter, and I'll try to pull this up on the video so we can. Okay, and swap this over to display capture.
Are each one of us going to the website?
No, I'm doing it.
Oh.
Yeah, thanks. That's a good question. Okay. I'm going to do duplicate so I can see in front of me what I've got up there. Okay. Display capture. Yeah. I need the trippy screen. Okay. Hello. Wake up. All right, here we go. So SYMOTT. Wait. Yeah, SimOtter.org. That's what I want. Is your tax dollars at work? So it's an NSF funded project. Let's do the symmetry tutorial first, just to show you the different. These are the 4 symmetry elements that we're going to learn about. You have reflection plane. The 5th one is the identity. We're not going to do anything with identity because it's just multiplied by 1. So we have the reflection plane, we have the inversion center, the proper rotation axis, which I've been talking about this morning with the water, and improper axis. So let's look at reflection. I'll do ammonia first. Okay. I'm going to turn it a little bit. This is how you would typically draw ammonia. And if you draw it this way, the plane of the paper is a reflection axis. But there's 3 of them. So that's the one that is the plane of the paper. And I can animate that reflection by showing how see, they reflect into each other. Now and this is a great website. So the nitrogen's also reflecting, just the front and the back of the nitrogen are changing places, and the other hydrogen as well. But then we also have this reflection plane. So every one of those NH bonds is in a plane of reflection. So you should be able to look at this molecule and see the 3 reflection planes. Okay? If we show all 3, you'll see that they all contain the NH bonds, right? So those are reflection planes, but we typically draw it like this, okay, with the wedge and the dash over here, okay? Now the rotation axis is pointing straight up. So let's look at the rotation axis, the proper rotation axis. Phooey, they don't have ammonia on here, but here's the water one. So here's the axis, straight up and down, and you can rotate it. See how it rotates? Isn't that beautiful? It's better than me standing in front of you. Okay, so that's the water rotation axis. Here's ethane. We're looking right down the rotation axis. Okay, and so we could rotate it this way. 1/3 of a turn. Okay, so let's do this. See, 1/3 of a turn. So that's why it's a C3. You take the full circle and divide it into thirds. So it's a C3 axis. We rotate 1/3 of a turn, and this hydrogen moves to there. So you can think of it as the labels as well. This label on this hydrogen goes to another hydrogen, and the label on that hydrogen moves here, and the label on this hydrogen moves there. Okay. Now, what about the other hydrogen? We could do it twice and move it around, or we could do it in the other direction. So the C2 and the C2 minus 1 just go in opposite directions. Or C3, sorry, C3 and C3 minus 1. Yes. Yes. Yeah, if it had 7 things around it, yeah. And this is how we typically draw ethane. You know, we've got that rotation axis, the threefold axis going up, so that's the z-axis. And then the x would come out and the y would go this way. We use a right-handed rule, so x cross y gives z. So that's the right-handed rule, x, y, z. So if z is going up, then x is coming out and y is going that way, x cross z. So it's a right-hand rule. Now, it has nothing to do with right-handed people being preferred. It has everything to do with, that's how they made the character tables, okay? So we need to use the same system they use to make the character tables, okay? So don't feel abused if you're a lefty, okay? Now, they could also have C2 axes that go 90 degrees to this. So this one is pointing straight out at us now. Okay, and if I rotate this, how far is it going to go if it's a C2? 1/2 of a turn. So just take that 2 and make it the denominator. So it's 1/2 of a turn. So this hydrogen up here, this one up here, will go all the way halfway around the circle and come over here. And everything else will move too. The carbons will go halfway around the circle and swap places. And so let's do it. It went the opposite direction as what I thought it would go, but it's, you see, that's a C2 axis, and this is a C3 axis, 1/3 of a turn, the C2 axis. Okay. And here's another one. Let me show this one. This one's off, the 60 degrees off, and it's here. So since this is a threefold molecule, if I rotate it 1/3 of a turn, I get another C2 axis. Okay. And if I rotate it another 1/3 of a turn, I get another C2 axis. So remember that question of Diamond that says, pick the CN, the highest CN, the C3. Are there 3 perpendicular C2s to the C3? And the answer would be yes for this molecule. And that sends you to a different part of the flow chart. So is everybody good with rotations? We're just going through the symmetry operations at this point. You good with the rotations? Okay. Inversion. Let's do ethane again. Let's get it up here like this. If I show the inversion center, it's on the center of mass always of the molecule. Now, everything goes through the center of mass to the opposite side of the molecule. So look at this, watch carefully. Okay, so everything inverts, even the carbon atoms. Everything goes through the center of mass to the other side. So directly across the molecule in all directions. Front goes to back, top right goes to top left, bottom left, and so on. Let me do it again. So that's the inversion operation. You're looking past the center of the molecule to the other side. So let's quickly show. A lot of people get this wrong. They think because methane is so symmetric, it has the center of inversion, but it doesn't. If I take this hydrogen and go through the center of the molecule to the other side, there's no hydrogen there. So it does not have an inversion. So you go through this, and this one goes through the center mass to a wedged over here, and there's nothing over there. So no, tetrahedral molecule, very symmetric, does not have an inversion center. Benzene. There's the inversion center. Okay. If I animate it, everything goes through the center of the molecule to the other side, and And basically you're swapping the labels on all the carbons and the hydrogens with the guy that's on the other side of the molecule. Okay. So that's inversion center. And let's do improper rotation. So we'll use ethane again. It looks interesting. So for rotation, let's think about what we've done. This hydrogen from rotation is connected to the other two hydrogens on this side of the molecule, right? If I do inversion, this hydrogen is connected to that hydrogen, right? It goes through the center of the molecule to the far side. But can I connect this hydrogen to this one with the rotation reflection operator or improper rotation? I can. So this is a way to connect this hydrogen to that one. So watch carefully. This has got an axis and a plane, and when I animate it, it rotates and goes down. So what I was talking about was this one. It goes over here 1/6 of a turn and then reflects down. So now I've connected this hydrogen to that one. And if I can connect a hydrogen to any other hydrogen in the molecule, then those hydrogens are equivalent. So they have the same NMR shift, they have the same partial charge, they have the same everything. They're chemically equivalent. If I can combine, or if I can get a hydrogen to exchange with another hydrogen by any symmetry operation, they're chemically equivalent. Okay. Yes?
What is it?
Order 12, that's the order of the point group. Yeah, so we'll talk about that in the future. Yeah, but so these are our 5 symmetry operations. Now, why is it C6? See, it has threefold symmetry. I had to rotate it 1/3 of a turn to get all the way over here. But if I only go 1/6 of a turn, I'm above this one. So I go 1/6 of a turn and then reflect down, straight down. So let's do that. 1/6 of a turn, reflect. So it's really 2 operations. It's a rotation, reflection, and some people call it the rotation reflection operator because they want to get away from moral language like it's improper, like you're doing something bad. Okay, that's what they started out with, proper and improper rotation. But some people are like overly sensitive, and so they're like, well, let's call it the rotation reflection operator. But that's just too long to say. And Zipf's law says make it short. Okay. Now, in order to find a point group, let's go back up here to home, and we have the symmetry challenge. And so this is your homework, to go through and work against, work these molecules like ammonia, and go through this point group flow chart over here. It says, does this molecule have an infinite rotation axis? Well, think of a linear molecule. If I rotate it, any infinitesimal degree, 1/infinity, the molecule looks the same. So linear molecules have a C infinity axis, which is the axis of the molecule. So that's another way of asking, is the molecule linear or not? Okay, so is this molecule linear? No. Okay, look, it didn't tell me if I was right or wrong. So I could totally get this wrong. Let's pick yes. Let's get it wrong. Okay. Yes, we'll just go down and hit yes. Check my answers. Wrong, wrong, wrong. Yeah, and it can show you why it's wrong. Okay, so let's start over. How do I start over? Pick ammonia. Okay, so is it linear? We would say no. Okay. Does it contain multiple C3 axes? I see one right here, but I don't see any others. So I'm going to say no. Pick the CN with the highest N. So this is a C3 axis right here. Okay. And so I'm going to say order 3, and I'm going to hit select. Are there 3 C2s perpendicular to that? Well, I'm looking right here. If I look like down that NH bond, it's not a C2 axis, because if I move those hydrogens halfway around, they'd be pointing up. They wouldn't go around. They would slide up and point up. And so there's no hydrogens up there. So that's not a C3 axis. So I have to say no. If it were planar like BH3, it'd be yes. Okay. Does this molecule contain a horizontal reflection plane? So that's horizontal to the vertical axis. The hydrogens would reflect up, and there's no hydrogens there. So I would say no to the horizontal reflection plane. Does this molecule contain 3 vertical planes? Yes. If I look down that NH bond, those hydrogens reflect into each other. And if I rotate it a third of a turn, I have another one. And if I rotate it a third of a turn, I have another one. So I have 3 vertical reflection planes. Each NH bond is in a vertical reflection plane. So I would say yes. You've determined the point group to be C3V. Ta-da! Checker work. Yay, all green. Okay, and then you can go through and you can show them, right? And you can play some of the reflections. Okay, you can hide that. So this is going to teach you all of these things. Show it. There's my rotation axis. Okay, here's my rotation axis. So go play with this flowchart, symmodder.org, and become good at identifying point groups. And that's what this next week's homework is, a bunch of point groups. Okay, so start working on this website and learning the flowchart. And you'll get a flowchart on the first exam or whatever we test this. Okay. I think. I haven't decided, but I think you. Yes. No, not at all. It's related to, what was today's quiz? Oh, it's point groups. Yeah. Okay, then I may extend the deadline. I'll extend the deadline to Friday. Okay? Yeah. Yeah. Especially because some people are new to it. Yeah. 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 Okay, yes. Someone send me a note to remind me.